All right. I woke up in the middle of the night and I was hungry as fuck. I kind of fucked up my routine a bit. But yeah. I'll fix it tomorrow.
CCNA course. And a huge shout out to Boson Software, the official sponsor of this CCNA course. They are the reason this can be made available for free, so I highly encourage you to go check them out. They have the absolute best CCNA, CCNP, labs, and practice exams. TCP/IP and OSI, networking models that define how we connect our computers. Without these, we wouldn't have networking. So in this video, we're going to watch it happen. We're going to follow a packet as it goes through a network and how it interacts with each layer. Let's do it. Okay, same scenario as the last video. Johnny wants some delicious Network Chuck coffee. So he needs to go over the internet to access networkchuck.coffee to order some coffee. Let's watch his packets go across the network and we'll analyze the layers as it goes across the network. Let's check it out. Now, I'll say it again. In reality, we're using the TCP/IP model, which is this. But for reference, I'm going to use the OSI model. So I'll add in those extra layers, the session layer and the presentation layer. Just gonna add.
I've already done this. So do you remember everything? Yeah, pretty much. Let's say Johnny wants to access networkchuck.coffee. We're going to explain the encapsulation and de-encapsulation process in detail, okay? Kind of what happens at the lowest level. Well, not the lowest, because the lowest level would be some behavior of bits that's predictable. But, okay. Johnny, let's say, wants to see if it can access this website first. So what does it do? It pings the website. It says hello. What happens here? Well, actually, this would cut out these layers. Why? Because a ping just operates at layers 3. And of course to 1, because everything has to travel. And then gets de-encapsulated and then re-encapsulated as it gets here. But what do we know about the switch? It doesn't know, it can't understand or read any of this. So when it considers a data link, what does it look at then? Well, we know we have to get to the internet, so what would be the MAC address that we're trying to reach? The switch? No, the switch is the intermediary, but it's a device that we have to reach. Yes, but that's implied because that's our only connection. The switch does the work for us. So, our default gateway, let's call it DG, is what? Our router. Okay. So, it will reach the MAC address of the router. What is the MAC address again? As in, like, what is it most comparable to? An IP, but at layer 2. Okay. So, we have the destination MAC address as the router and the source MAC address as Johnny. Every device on a network, every network device, or networked device, all of these has a MAC address. Okay. So it re-encapsulates, does it? Well, it has to. To read, it always has to de-encapsulate. So it starts from the physical, reads the data link, and then sees that and then re-encapsulates it, which would just be the destination. And the source would be what? I guess still Johnny or the switch? Wait, am I retarded?
Add those in there, stack them up. And if you want to follow along, which I highly encourage you to do that.
Wait, am I retarded? So, say Johnny wants to reach a server on a different network. He's connected to a switch. Obviously, he reaches his default gateway. My question is, the interaction between the switch and the router, the default gateway, obviously the switch will de-encapsulate, read the source and destination, and the source destination would be Johnny, right? And the source MAC address would be Johnny. The destination MAC address would be the default gateway, right? But what does the switch then do when it de-encapsulates and then it re-encapsulates? Does it change the source MAC address to the switch itself, or no? It's still Johnny. And why is this confusing to me? Johnny sends packet. Source IP. Here's the important part. The switch does not de-encapsulate through frames the way a router does. It doesn't open the packet. Right. Right. So you'd almost say, yes. It just has a MAC address table that it considers. So would you say re-encapsulation, encapsulation and decapsulation is that a smart layer 3 function, or how would you describe it? Could you maybe better explain why this is an easy way to remember this? Right. An easy explanation is a router has to consider different networks. So there's more to consider than just MAC address. So it has to de-encapsulate the frame to look at the IP packet and change that. Where a frame is a header and trailer often, right? So if a switch receives something, we know it's part of it. It has to send it inside its LAN because a switch doesn't route. So in other words, it doesn't have to de-encapsulate the frame because all it can consider is the frame. The router, though, has to often reach a different IP packet and has to look at its ARP table, right? And
that's called encapsulation, giving our routing layer that it's now stuff. Awesome. So real quick, a 1,000-foot view. What Johnny had to do is he had to use the entire TCP/IP suite, encapsulating all this stuff down into a frame. And then he sends this frame across the physical network, across Ethernet cables and such, touching each device, a switch, a router, another switch, and then
Ugh.
finally arriving at networkchuck.coffee. Networkchuck.coffee took that frame and then de-encapsulated the entire thing to look inside and see what was meant for the web browser, the application information. And of course, in this case, the data was a request for his web server. Johnny's wanting to buy some coffee. And Johnny's like, hey, I'm trying to get to the homepage of networkchuck.coffee. Can you give me the homepage so I can shop? So the web server reads that request, which is inside the data, and the whole process starts over again. The networkchuck.coffee server encapsulates all the information into a frame, sends that to the switch sends it to the router to the switch to Johnny, and this is what Johnny receives. All right, quiz time. I hope you have your coffee ready because these questions I chose are kind of difficult. One is from the old CCNA, and one is from the old CCNP route exam. So let's see what you got. Let's go. Question number.
Which of the following functions are performed by the application library assignment? Select 3 choices. Determining whether adequate resources exist for communication. Ensuring error-free data delivery between devices. Yes, that's one. No, that's transport. Management between application, that's one. I think F.
Number 1. Layers, and I'm gonna go to layer 7. The one we didn't select down here. The one we didn't eliminate. This is part of the presentation layer, which is layer 6.
I forgot we were talking about OSI, not TCP,
But
right?
as part of the TCP/IP model, layer 6, layer 7, and even layer 5 are all clumped together in the application layer.
Right.
And if we had talked about the presentation layer in detail, you would have known that this is not it. But we didn't, so it's okay if you didn't get this. Now C and E, we probably could have just guessed that without having even known anything about layer 7. Managing communications between applications, directing data to the correct program. Program is another word for applications. A would have been a bit more fuzzy, but just from the process of elimination, we would have got that one. Question number 2. Which of the following relies on a 3... So for example, CCNP level question from the old CCNP route. In the route exam, I failed that 3 times. 3? No, 2 times. It was a tough exam. Well guys, that's about it. If you like this video, hit that like button. Like more, jumping into the upper layers, the application, the presentation, the session, the transport. We're going to dive deeper into those.
Okay. Only thing I think I have to remember here is that, like, when we talk about, like, functionality, what layer does what, consider if we're talking about OSI or TCP/IP, a switch obviously just takes a frame and looks at its MAC address, its content addressable memory. Wait. and it just forwards that frame. Now again, a frame. Remember that, like, realistically, the packet looks most similar to something like okay. Now the frame itself is shown here.
Huh. Look, it's for me too. This is my IP address. Awesome. He'll then de-encapsulate it, giving our router directions. We're saying, hey, Mr. Router, here's the case we have the source MAC address, which is
but it would start there, obviously. Like, if we say like this, we could view it like this. Whenever someone receives something, it goes from here to here, right? So you have layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, and then layer 7, application, which deals with things like HTTP, DNS, fucking, you know, what's that thing called again? Screening service. What's it called, man? It's like a Windows recording service. I forgot.
is Johnny's MAC address. And then we have the next stop, the destination, which is our...
So Johnny sends as a, what would you call it? Ping would be an IP packet. HTTP would be a... Well, everything is essentially called a packet, but it would be a layer 3 at most, the highest layer. So has a destination IP, source IP, of course, destination MAC address, source MAC address, and then what about layer 1? Layer 1 is just the traveling of this information in a modulation scheme, and as in electrical signals, if it's an Ethernet cable, or are radio waves not electrical signals? No. What kind of question is that? Or maybe in some way you could argue they are? Obviously not, but like, what is the correlation? Electromagnetic. So... Electricity makes the field, and changing fields make waves. Huh.
A router. And that's pretty much it. We've encapsulated all the layers down to a frame, and now we can send that frame over the physical layer, the Ethernet cable. So he hits the wire, and boom! And actually, he's up here. So he goes from Johnny to the switch. Let's watch it happen in Packet Tracer. If we step forward in time, we see that frame go to the switch. If we open up that frame, we're only seeing layer 1 and layer 2 because the switch can't see anything else. All these layers right here have been encapsulated down into this frame. And when the switch receives this frame, he's got this bulky envelope, but he only opens the first envelope. And he opens it up and goes, oh, well, let's go into this MAC address, which if I look in my CAN table, my MAC address table, I can see that MAC address belongs to this port. I'm gonna send it out this port. That's where the router is. See right here, he looked it up and Fast Ethernet 06 is the port that the router belongs to. Let's step forward in time and watch it happen. Boom, it goes out to the router. And boom, it also does it here. If we open up that message, the router did indeed receive a frame. And he made sure that it was for him, it came to his MAC address. He will then do the opposite of encapsulation. He'll de-encapsulate it, which basically means he opens the next envelope to see what the next layer says. So he takes a peek at layer 3. And at this point, we're dealing with the packet, with the layer 3 header, the layer 4 header, and the data. The router looks at the layer 3 header, sees where it needs to go, what is the destination IP address, looks in his routing table. He's like, yeah, I know where that goes. I've got my map. I'm a layer 3 guy. And he then proceeds to send it out to the switch. Now, something important happens here. Remember, the switch can only deal with layer 2. If you recall from our previous videos, the router has to somehow tell the switch how to get to networkchuck.coffee. He has to tell him his MAC address. Otherwise, the switch will have no idea where to send it because he can't see IP addresses. So after the router learns the MAC address of networkchuck.coffee using ARP, he encapsulates his layer 3 header, which is the IP address information, inside a new layer 2 header. And he changed the source and destination MAC address. And he had to change it because before, the message he received, the source MAC address was Johnny and the destination was himself. Now he has to change it to being the source is himself and the destination is networkchuck.coffee. So he encapsulates that, it's now a layer 2 frame, and he sends it up to the switch. We'll step forward in time and packet tracer here. The message arrives at the switch. If we open that up, here we are again, switch eyes. We can only see frame directions for the switch, telling the switch where to send his message. So in this case, we have the source. Source Mac. This is episode 5 of my free CCNA course, and a huge shout out to Boson Software, the official sponsor of this CCNA course. They are the reason this can be made available for free, so I highly encourage you to go check them out. They have the absolute best CCNA, CCNP, labs, and practice exams. When you watch a YouTube video like this one, what happens?
It's a good question. Well, what happens? Well, UDP is being used for sure. You're getting a lot of GET requests. Well, not a lot. It's not. It's usually done efficiently, such that the video format here, the MP4 file or whatever, well, it's done in JSON or I don't know, would be shown to me. Of course, I'm going up to application layer from, encapsulate it. So we have our requests. So how does it know that? How does our computer know that? Through network stack software. What do you mean? Like, it knows that we're accessing a web server. It knows the destination. It knows we're using a Chrome browser. It knows to use GET to request that, create your session, transport TCP, UDP, create your IP packets, our next MAC address, which is our default gateway in this case, which is right there for me. More details.
What's happening in the network? In this video, we're going to find out. We're going to focus on the upper layers of the OSI video, like this one. What happens? What's happening in the network? In this video, we're going to find out. We're going to focus on...
Explain what you're looking at. So Johnny wants to watch YouTube, right? Again, always remember, like, most networks have it all in one device. So there's a switch, router, and modem. No, the modem is still separate usually, and a wireless access point. So it does all those functionalities. Again, at the end of the day, these are functionalities. And in enterprise networks, they're separated. So we assume this is an enterprise network where we only consider these people. So Johnny connects to the switch using obviously Ethernet. Which one? What type of Ethernet cable? 1 gigabit, 100 megabits per second, 10 gigabits. Those are the most common ones, I guess. Most of the time, you're going to think and consider 1 gigabit per second nowadays, I think. What else? Then it's, in this case, is it crossover or straight? Straight, I think. The switch knows to, I think, computer and router is crossover though. But usually it's, technology is something that's called auto MDIX. So devices know to use that technology to adjust. That's good. Okay, so the application, you're probably using HTTPS, which is Hypertext Transfer Protocol Secure nowadays. How do you check? Well, you can check your browser. HTTP. It's actually obfuscated after you've entered the web page, but to actually create the secure connection, you see you're accessing it here. And this is, what is this then? This is a protocol in itself. It's a protocol, right? It's the interconnected web or something. An information system that runs on top of the internet. It's the collection of websites, hyperlinks, and resources you can access through browsers. Okay.
It's on the upper layers of the OSI model.
So what is this? So you have your data request, right? You're trying to access something. You're using an application. This is why you create your request. How do you know what to create? Honestly, I say it's OSI, but usually it's just the Chrome, the browser you're using. It's optimized to ask for these things, right? Then you present that. What does that mean? That means that you encode it in a specific Unicode format, or protected TLS, SSL. In this case, what are we using? TLS probably. And then you create our session, which is a TCP session, which is a handshake that's syn acknowledge. And it's from YouTube side, actually. Forgot about that. Well, this is YouTube sending something then, I guess. Or like what?
Model the application, presentation, session, and transport layers, and see what happens when we try to watch a YouTube video. Let's get started. In our last video, Johnny needed coffee bad, and we watched how his internet traffic, his network traffic, would go across a network, across the internet, and get to networkchuck.coffee, where you could place an order for delicious coffee. And it is good, trust me. We dive deep into the OSI model, a model that describes how a network can work. When we watched this, Johnny's computer took his application data and threw it down the layers of the OSI model, going from segment to packet to frame, a process we call encapsulation. And then it fired electrical signals, it probably doesn't make that sound, across the physical wire, going across the network, the internet, until it finally arrives at networkchuck.coffee, a server that hosts the website. And here the process is actually reversed, going from frame to packet to segment, a process we call de-encapsulation. And this whole process is amazing. But up until now, we focus hard on the network, data link, and physical layers. We haven't spent much time in the upper layers, application, presentation, session, and transport. Until now, we're going to look at all that right now. If you've watched the previous videos, you should have a basic understanding of a switch and a router and what it does when your internet traffic hits it. If you don't know what that is, then go back and watch those videos. But now we're going up, and Johnny already has his coffee. He's already ready to go. Now he wants to watch some YouTube videos. So we're going to pop the hood a bit and see what happens when Johnny's web browser tries to access YouTube and how the application, presentation, session, and transport layers are involved. You might need some coffee for this. Take Johnny's advice. Let's take a look at the application layer first. So Johnny fires up his web browser and he begins to type in youtube.com, and this is where the OSI model comes into play, the application layer. And also keep in mind this does apply to the TCP IP model, the model we actually use, which is the same as this, except we don't use the presentation and session in that model. But the concept of these layers does not go away in the TCP IP model, which is why we're going to talk about them right now. And the application layer is kind of the portal, an interface for a program on your computer that needs a network, like your web browser, or a video game that right now. And the application layer is kind of the portal, an interface for a program on your computer that needs a network, like your web browser, or a video game that you play online. If that application needs to interface with a network, it's going to engage the application layer of the OSI model. It's sort of the gateway to the next two layers, the presentation and session layer. So Johnny's web browser takes the data it wants to send to youtube.com, which in this case would be like, hey, I want to see your site. So it'd be a GET request, get me that stuff. And it sends it down to the presentation layer where we get it prettied up. Time to get it dolled up and ready to go. What does that mean? Well, the presentation layer is responsible for making it presentable. Two of the main things it's going to be worried about is data format and encryption. Now, data format, what does that mean? One way to think about data formats is to think about file types. Let's say I send you a document. It's called mydocument.pdf. When you try to open that document at your computer, what happens? Well, it opens because you've got programs and applications that know how to use PDF documents. That's the data format. Adobe Acrobat, even most browsers can open up PDF documents no problem. It's a common format that we've all agreed to use for things like this. But if I were a weirdo and I put my data in a format that no one even knew about, like .networkchuck, and I sent that to your computer would be like, I don't know how to view. I don't know what this is. So that's why we have these file types, these data formats. Things that we all pretty much agreed we're going to put things into this format so we can all kind of play with and read. And with web browsers, what's a file type we see all the time? HTML. The presentation layer would take our data and put it in a format that we all pretty much understand. Put that to a .html file. And when YouTube does send me a .html file, it knows how to open that. That's what the presentation layer does. So HTML, XML, JPG, a image data type, image data format. That's what the presentation layer does. We can also use encryption at the presentation layer, making sure our data that's being sent back and forth can't be seen by, well, hackers. A common one you might see is SSL. Secure socket layer. That's done at the presentation layer. So once the presentation layer is done with our data, he's made it look pretty, putting it into the right format. He may have encrypted it so someone can't see it. We then move on down to session. The job of the session is to open up the communication, to start the conversation between the web browser, Johnny's application here, and the YouTube server, and make sure things have been authenticated, make sure conversation is smooth. Now, keeping in mind all this stuff is still going through all the other layers, and a bunch of things are happening here. But logically, the session keeps the communication open. And what I mean by that is that at the lower layers, at the network layer, we're going through routers, at the data link layer, we're going through switches, all kinds of crazy stuff is happening down there. But to the session layer, it's one conversation. Let's keep this thing going. And when it's done, he tears it down, ending the conversation. And the session layer does this for any communication that the application has with anything else. Maybe it's not just a web browser talking. Maybe you have Spotify running, talking to the Spotify server. It's managing all those different sessions on your computer. Some popular protocols you might see at the session layer are L2TP, or the layer 2 tunneling protocol. You'll see this a lot with VPN connections. We've got RTCP, the remote transport control protocol, which this actually helps set up phone calls. And speaking of phone calls, video calls, the H.245 protocol, which helps set up video calls. And of course, proxies. We have these SOCs, proxies operating at this layer. When you're trying to hide yourself as a hacker, or just as a person who values their privacy, you will use a SOCs proxy, which operates at this layer to bounce between different hosts to kind of muddy up who you are. This is not an exhaustive list, but this is one of the most popular protocols you'll see at that session layer. Now at this point, we've covered the application layer and what it does at a high level view. Application, presentation, session, keeping in mind that all of these are just one layer in the TCP IP model, just the application layer. So
Right, I don't know why I said TCP session before.
we get the data. This is not an exhaustive list, but this is you making phone calls, video. Do this a lot with the different sessions on your computer. So EP, the remote transport control protocol, which this actually helps set up phone calls. And speaking of phone calls, video calls, the H.245 protocol, which helps set up video calls. And of course, proxies. We have these SOCs, proxies operating at the this layer. When you're trying to hide yourself as a hacker or just as a person who values their privacy, you will use a SOCKS proxy, which operates at this layer to bounce between different hosts to kind of muddy up who you are. This is not an exhaustive list, but this is one of the most popular protocols you'll see at that session layer. Now at this point, we've covered the application layer and what it does at a high level view. Application presentation session, keeping in mind that all of these are just one layer in the TCP IP model, just the application layer. So we get the data ready, we pretty it up, put it in the right format, encrypt it maybe, and then we get the communication started. We start talking to somebody, we get that session open. But in order for that session to actually open up, we have to send it down the other layers. And now we're at the transport layer. We're getting somewhere, literally. The transport layer is where people who love networking start to pay attention. Application layer? Nah, that's for programmers. Wait, did you say transport? Now you got my attention. This is where we operate. The session layer sends our data down to application layer? Nah, that's for programmers. Wait, did you say transport? Now you got my attention. This is where we operate. The session layer sends our data down to the transport layer, and now we're worried about, hey, how can we get this data to the other end, to the other server? This is kind of like sending a package to someone. Like, let's say I want to send a package to you, and at the application layer, I'm going, okay, I want to send this, and this cable, this pen, and this coffee mug full of coffee. Then I'm gonna put it into a box. I'm gonna make it all pretty, tape it together. Okay, done. Now, how do I get it to you? I gotta send it to the next layer, which might be shipping. Do I use UPS? Do I use USPS? Do I use FedEx? DHL? Who's gonna take it for me? What method am I going to choose? How am I going to transport it? Transport layer, ha, see that? And with the transport layer, instead of choosing a shipping carrier, we're gonna choose a protocol. There are two main transport protocols we focus on. There are others, but these are the two main ones we see all the time. We got TCP, probably heard of that guy, and UDP, probably heard of that guy. And at this point, we have to ask ourselves a question. And when I say us, I mean like the web browser or the application. Do we want our data to get there really, really fast? Or do we want it to get there safely and make sure it actually gets there? If we want it fast, that's going to be UDP. If we want to make sure it reliably gets there, it's going to be TCP. Let's take a look at TCP first. Let's say we do want to get our stuff there reliably. The reason it's so reliable is because TCP is kind of naggy. What I mean is that when TCP is communicating, let's say YouTube sends me a file, like an HTML file, like maybe it's the homepage, so homepage.html. Before it sends me anything else, it waits to see if I got it. It's like, okay, did he get it? If I don't say anything back, he's like, hey, Johnny, here it is again. Did you get it? And he waits for me to say, yes, YouTube, I got it. And then he'll continue to send me more data. But it's that verification process, that reliability, that makes TCP pretty cool. It makes sure your data is received. And if it doesn't receive a confirmation that you got it, it'll send that sucker again. And another reason that TCP is reliable is that before we even begin to send data to each other, we have to get to know each other first. So YouTube will go, hey, I want to send you something, Johnny, but I have to make sure we're friends first. Let's do a three-way handshake. And that's what it's called. The TCP three-way handshake, which is all about setting up that connection before we start exchanging data, which works like this. YouTube will say, hey, Johnny, how you doing? My name's YouTube, which we'll call a synchronization message. Johnny will respond and say, well, great to meet you, YouTube. This will be our send ACK message. And then YouTube responds with a ACK, which send means synchronization, ACK means acknowledgement. And once this formality's out of the way, then they can communicate with each other, but this has to happen. And so this is a bit more involved. Oh, and by the way, TCP stands for Transmission Control Protocol, with a strong emphasis on control because it wants to control every bit of that communication. Whereas UDP, it's a little crazy. Do you want to know why UDP's fast? Because it just doesn't care. It doesn't care if you get the message. It doesn't care if you get the package. It's just going to keep on sending stuff. It doesn't wait for verification. It just goes, blah. Here you go, 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 here you go. Ah, crap. It just sends. So no, how you doing? Nice to meet you. No, YouTube just blah, sends and sends. Doesn't wait for verification. And hopefully you get it all. So now when Johnny's trying to watch a YouTube video, which one is used? TCP or UDP? Both. It's actually using both. Check this out. I'm going to fire up Wireshark, which is a tool we can use to capture our real network traffic. So watch this. It's awesome. I'm going to start capturing on one of my interfaces here. And look at all that. It's just a ton of stuff. So it's capturing everything. Now I'm going to go off and watch a YouTube video. Let's go. Boom. All right, let's pause that and let's take a look at Wireshark and see what happened. Let me stop this capture here. Now I captured all my internet traffic and my computer's talking to a lot of things all at once. So I need to filter that a bit. Now this looks crazy. I know, a lot of stuff going on, but we'll break down just a few things here. First of all, this IP address right here, 173.194.191.167, that is the IP address of YouTube. So when I open up my web browser and I hit that URL, that's what I was going to. Notice the source is my IP address right here, destination is YouTube, and look at the protocol. We're using TCP, the Transmission Control Protocol, reliability. And notice here's a three-way handshake right here. Got my SYN, my hello, how you doing? My SYN ACK from YouTube, I'm doing fine, I'm YouTube. And then the ACK from me. And then of course a lot more stuff going on down here. But I want to scroll down and show you something else. I said we're using both, and I wasn't lying to you. If you scroll down a bit, I mean, there's a lot of things going on. We'll keep scrolling, until I finally made it here. Okay, cool. Notice it went from TCP, and it changed everything to UDP. Still talking to YouTube. It's still me talking to YouTube right here. But the protocol switched over to UDP.
Okay. Okay, let me try to explain everything that wasn't too clear to me now, in my own words. Okay. So, first of all, what's this whole confusion that you have about encapsulation and de-encapsulation? I don't know, it's not really a confusion, to be honest. Think of it like sending a letter. How so? Because when you send something, what do you do first? Okay, you have your paper. This is like the application you're using. You write something, right? You write it. What do you do then? You encapsulate that. Literally, this is the most visual way that you can understand it. Inside a envelope. Okay, so this would be layer 7, and this would be layer 6, and then I'll see it's not, and then this would be theoretically layer 5, whatever that may be, fucking a basket for extra protection. Okay, but so what? Now everything is sent as a frame over the internet? Well, what? This is silly. You send something based on where it's going. So if you know, you create a packet, okay, but if you are connected to your switch, that connection, this is obviously always going to be a single, well, one network. So really, you could argue that it's a frame. Really, because it's going, we know that this has to go towards somewhere on the internet. It has to be traveling as a packet. But when the switch receives it, obviously it just interprets it as a frame. And by the way, a frame, quick refresher, because why not? It's just, like, we can also view it like this. Your data transport network trailer or header, and then trailer. There's also a trailer that gets added to the back here, and this is the frame. Now it's not really readable, man. What the hell? The router obviously considers this heavily. Why so? Because it has to route to different networks. It has to know how to reach it via multiple hops to finally reach its destination IP. Keep in mind the IP is a global phenomenon. This is supposed to be a planet. It's a global unique address. Well, your public IP is. And whenever you try to reach a web server, like YouTube.com, that's what you need. Okay. So again, what I'm saying is the way you call it, frame, packet, this, that, this, it doesn't matter. Just know that things travel as bits and are sent as, well, the information doesn't leave. So really, you could argue that, I mean, we're sending an entire segment or a wait, hold on.
Why? Well, when Johnny sends a request to watch a YouTube video, and obviously I'm changing myself to Johnny now, YouTube doesn't just send a video, but it sends a web page as well. So like we look back at the web page here. It's loading all kinds of stuff. Like we got the menu right here, we got suggested videos over here, sign-in stuff, buttons, graphics, all kinds of stuff. This is all just a regular web page. In fact, if we look at the developer tools, which you can do in any web browser, we can see that it is indeed an HTML document. So YouTube sends the HTML file and along with other stuff to build out this web page, but then
How do you open developer tools again? What? I pressed F12. Control Shift L. Oh, it's still showing there. What? Might be this overriding what I should be doing or what should be happening.
Then it starts to play the video. This is when it switches from TCP to UDP to send data. But why does that video need UDP? Why couldn't it just use TCP? I mean, what's wrong with having reliable transportation for a video? Well, think about when you're watching a video, like let's say this video right now. With UDP, you're just getting this data, bam, 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 bam.
But wait, that's annoying, man.
Hello everyone, I'm back with another video. In this video, you will find all the extensions in your Opera GX browser, and simply click on this extension option, and here you will find all the extensions. Here you will find developer mode. Simply enable this developer mode. When you enable developer mode, here you will find few options called load unpacked and pack extension. If you want to load unpacked extension for your Opera GX browser, simply click on this option. From here you can select the extension or the tools you had developed for Opera GX browser. You can also use pack extension to load your developed extensions and the tools on Opera GX browser. And here we have extension root directory. From the browse option, you can browse your root directory, and here we have private key file. This is optional, so if you had created a private key file for your extension, then you can simply browse that private key file. Then you can simply click on pack extension. So this way you can enable developer mode on Opera GX browser. So that's it for this video.
Opera GX. To go ahead and find in some codes in here or to view more functionalities for this, click onto this logo here, onto the upper left, and you should be able to find in developer. So you should be able to see developer tools in there, and by that it should open some functionalities for this. Click onto this logo here, onto the upper left, and you should be able to find
Inspect React element, I guess. I don't know, bro. What else I could do? Yes.
And bam, the video's coming at you. You might miss a few of those packets. So let's do a clip, for example. Let's say I go, that is delicious coffee. But maybe your internet connection's bad and you drop a few packets, so it might look like this. There's coffee. Now that's not great because you missed something. So you might think, well, we can prevent this from happening by using TCP, right? It'll make sure you get stuff. It sounds good in theory, but here's what would happen. There's coffee. That is delicious. You see, for real-time applications like that, watching a video, watching a live stream, gaming online, it doesn't make sense to resend the same thing because once that thing's missed, it does no good to get it later. I mean, this has happened to you before, right? Like you're playing an online game, you're running, maybe your internet connection drops for a second, and you're suddenly 15 feet ahead. It would make zero sense to try and have that data sent back to you and throw you back 15 steps so you could walk that hallway. No, you'd already be dead because someone shot you up there. So TCP is great and it's used for most things that don't require that real-time interaction, but when we need to have things quickly and fast, and we're retransmitting things which would not make sense, that's where UDP comes in. Now there's one more thing I want to touch on with the transport layer in TCP and UDP, and it's these numbers right here, 443 and then 57095. They're crazy important, but what are they? Let me show you a problem we might have if we didn't have those numbers, which we call ports, but we'll cover what those are in a minute. When we want to watch a YouTube video, we have to access their server, which means we have to go over the internet and hit their IP address. This will be using the HTTP protocol, and in pretty much all cases now, the HTTPS for secure protocol. But what if that YouTube server wasn't just doing a website? What if it also had FTP, a file transfer protocol server? What if it had SSH and RDP? Both protocols that we can use to access a server remotely. So if I wanted to SSH and log into the command line of that YouTube server, how do I tell it that? How do I go to the IP address and say, I want to SSH and not just I want to watch a video? That is what those port numbers are for. If we look back at Wireshark where we captured our network traffic, look at this first message, which is from me to the YouTube server. I'm using the TCP protocol, and here's the from port. We'll talk about that here in a moment, but the to port is 443. You may already know that port 443 is the port that's commonly used for HTTPS. So in your web browser, when you type in HTTPS, youtube.com, you're saying you want to access this server IP address on port 443. It could also look like this, the IP address with a colon after that and the port. So I want to access that server, the IP address, on port 443. Those ports allow us to run multiple services on one server. So one server can be a ton of things. It could be RDP server, SSH server, FTP server, web server, gaming server. You can open up other ports, other windows into your server. And no, I'm not talking about Windows Server. It could be Linux, I don't know. Another well-known port you might know about is port 21. Port 21 is commonly used as FTP, SSH 22, RDP 3389. If you go to Google and just type in common ports, you'll get a ton of information. I'll look at this Wikipedia article real quick. And if you scroll down here, notice we have our port number protocol, and then we have TCP and UDP. Some ports are only TCP or just UDP or can use either or. And notice as I scroll down, there are a ton. Just a ton. In fact, we have available ports 0 through 65,535. But as far as these well-known ports, which are listed below, ports 0 through 1023 are reserved for those. Now, you don't have to memorize all of them, but it is important to learn the key ports. Ports that you'll see used a lot. So 22 for SSH, 23 for Telnet, 25 for SNMTP, port 80 for HTTP, 115 for SMTP, 12.
Telnet. NTP.
3 for NTP, so just a lot of stuff out there. So looking back at Wireshark, we got this destination port of 443. We know what that's for. It's for HTTPS. We're accessing the web server of YouTube. Awesome. But then what's this big number over here? 57,095? Obviously not part of the well-known port range. What is this for? Well, network communication is a two-way street. So when I'm communicating with YouTube and I'm saying, hey, I want to access your web server. I want to see some videos right now. Right now. That's going to send that video back to me. That's going to send that video back to my IP address, which if I'm only accessing YouTube, that's fine. But I'm not only watching YouTube right now. Often I'm listening to Spotify. So Spotify's sending me stuff too. I'm browsing a few other websites at the same time. I mean, we all have like a million tabs open, right? So they're sending me data at the same time. I'm receiving a lot of data from a lot of different network applications. So that port number, 57,095, it's kind of like my from address. When I say, hey, YouTube, send me back a video, I say, hey, send it back to me on this port so my application can get it. Because I'm doing a lot of other stuff right now. You're not the only application I'm talking to. Sorry, YouTube. So essentially, my web browser pulled this number out of the air. It's temporary, often referred to as an ephemeral port. I love saying that word, ephemeral. Ephemeral. Say it, ephemeral. Say it out loud right now, ephemeral.
Ephemeral.
It's temporary. And when YouTube sends me that video, it responds back to that port, my IP address with that port. If I look back at Wireshark and I stop filtering just by YouTube traffic and I look at everything I'm talking to right now, you can see that my computer's using a bunch of different source ports. 52015 for this particular server I'm talking to. 51931 talking to this server. And here's an example of the server talking back to me on my port. So 443 talking back to my ephemeral port here. So let's walk back through what just happened with YouTube. Let me erase some stuff here. My communication with YouTube used both TCP and UDP. So after the application layer got it all pretty and ready for me, boxed up with a bow on it, my web browser decided to use TCP on port 443, and we take that information, that segment, and give it to the network layer. Now what does he do? Well, he handles the IP addresses. So now it kind of looks like this at this point. We have our data from the application layer, we have our layer 4 header from the transport layer, which is basically saying we're using TCP port 443. And the network layer is going to slap on a layer 3 header, turning this into a packet. And it's got a destination IP address of 173.194.191.167. Blah, blah, kind of hard to see there. You know what it is. And then it goes on down. You know the process. If you go back and watch our previous videos, you know what happens. Oh, and of course, this layer 4 header also has the source port, of 57095. And when it goes through the internet and finally arrives at the YouTube server, and it gets to the transport layer will go, oh, hey, this is coming in on port 443. This is our web server. Let me hit this up to the web server application. All right, quiz time. Hope you're ready. Hope you have your coffee ready, because this is gonna make you think. These questions are brought to you by Boson XM, the best practice exam software out there for any kind of Cisco, CCNA prep, CCNP prep. So if you're getting ready for your exam, you might want to get Bose on and see if you're ready. But let's see how you're doing right now. This will be a simulator question very similar to what you might see on the exam, so I'll go ahead and launch this right now. Ooh, look at this. So select the application.
DNS depends actually. I think it's both. DCP, TCP, FTP, UDP, HTTP. No, TFTP. Okay, that's UDP. SNMP is UDP. HTTP is TCP for sure. FTP. Huh. It's a while ago, man. Fuck me. Okay, so what do you know for sure? TFTP is UDP. Simple Network Management Protocol has to be quick. I think that's UDP as well. Simple Mail Transfer Protocol. Yeah, okay, I think. Hold on, was I right? So, FTP, Simple Network Management Protocol. Yes, TFTP, DHCP. Yes, DNS is both. Okay, so kind of. Like, I knew DNS was both. I think maybe the one I wasn't sure about was DHCP, but I guess it makes sense that it's supposed to be quick.
Which of the following ports is used
by TFTP? 69. That's 69.
by TFTP? Know this. I know it's going to be UDP exam. Today, if you can vote those protocol uses.
And UDP also.
Video.
Hey, I've got a question for you. Can your network survive a pug?
Oh, hell no.
Okay, what about a baby? If it can't, if you can't afford to lose one link or one switch or one router, you're doing it wrong. In this video, I'm going to show you 2 network architectures that can help make our
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick. What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick. What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick. What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
Okay, let's begin, shall we? Let's do just a recap of what I just consumed. Start. I'll put my timer at 50. Go. Alright, so one thing that I struggle to kind of understand really at like an intuitive level is so when you access this, what's going on? So usually before you even access anything here, there's a HTTPS connection that establishes. Now this is essentially if you were to analyze your web traffic as you're watching a kind of YouTube video. The first thing you'll see is a TCP SYN acknowledge and then acknowledge. Now if it's the web server or like who is actually doing this? Like how do you even remember or know? Remind me again the utility of a server. A server is any computer providing a service. What do you mean service? Like, okay. We use applications, right? Does every application need a server? If it needs collaboration and updation and etc., yeah. There's local applications, alright? Sure, yeah, for sure. But anytime that we talk about the OSI, we consider things that require collaboration, connectivity, right? So yeah. But usually you'd see TCP first, and then you'd see UDP traffic. Now, I liked the kind of way he presented it with like, why not use TCP for video? Because it would just be it wouldn't be effective. Why? Because it's too high, it's too constant. What are you saying? I'm saying if you use UDP for video watching, you'd miss a lot. Like it would be like, ooh, I got this snippet of like audio, then there would skip a whole bunch. No, we wouldn't skip a whole bunch. But it would almost buffer. And then the thing with UDP is, UDP non-reliable. But when we consider the importance of each, sometimes you need more speed than reliability. Now again, every device, let's look at it like a stream of data. Everyone is using UDP, everyone is trying to access this web server. Now the web server itself, what is the server icon again? And just in general, server icon, so it's like, it's more like this. It's better. How does it know to reach you specifically and that specific application? That's a good question. So, like, it can reach you if it has the destination IP of what? Of my device? No, of your public IP. So, what has that? That would be your router. Yeah. Okay. So I repeat. Let's grab this actually. Then it would be able to reach you. But then what? Aha, this is where it gets kind of tricky. Your router retains a kind of, what is it, NAT table? And this table essentially maps the requested things that you asked, like maybe port 443, and this destination IP, which would be the server, obviously. I think, right? And then the source would be some and then your IP. And that mapping lets it know where it needs to send to and who requested what service. So that's all handled by this guy. Yeah, because again, all this cares about is creating the bridge that connects the server to the PC. And again, you call these segments. Now again, segments you just have to remember that everything that travels over the internet usually gets standardized and called a packet, or over your LAN or over your network, whatever. LAN or network? What's the difference? A LAN is like your house network. It's a small network that's of one entity, one person. A network itself, again, it's funny because you have to remember that at the end of the day, even a /32 equals network, but it's a direct, often, what's it called? One-to-one connection? No, peer-to-peer? No, it's what else? Filters. Overall, your device, your network, you're obviously, like, you have to remember that your computer, like, at all times is doing a shit ton of things at once usually. Like what? Like the average person has dozens of web tabs open, and each of these has a TCP, UDP type shit going on. maybe ARP is doing something. You're like trying to get the MAC address of something. Maybe even you're just pinging. So you can see ping. Maybe what else? There's more than this, right? Yeah, obviously, but.
Our networks. Awesome. And a huge, massive shout out to Boson Software. They are the official sponsor of this free CCNA series. And if you're trying to get your CCNA, which I assume is probably a lot of you, Boson has the best labs, practice exams, and now the best courseware you can find. And if you're trying to get your CCNA, which I assume is probably a lot of you, Boson has the best labs, practice.
You administer the network shown in the topology diagram. Please click Launch Simulator to view the configuration of the routers and the host devices and to answer the following questions. Why is router 1 unable to form an adjacency with router 2? Select the best answers. What is adjacency again? It's like a neighboring friendship type stuff, I think. Router 1, router 2. What's the most likely? Most likely, most common. Obviously, I can't look at what's going on, but this one is very common. The hello times don't match.
Practice exams, and now the best courseware you can find for the CCNA. I'm actually giving away 3 copies of their courseware and labs in the link below, so enter that contest. It ends tomorrow, Friday, so hurry up.
Now, before I show you what a good network design looks like, just a beautiful, delicious one, let me show you a bad one first. As you're working towards becoming a network engineer, you're going to see some bad networks, and it's your job to identify why they're bad and how you can make it good. Now, to find a bad network, you don't have to look very far. Look in your house. I'm not kidding. Your home network sucks. No, I know a lot of you probably have an amazing home network, and comment below with what you have. But for a lot of you, if you ran a business out of your house and you use that home network, it just die. Your business would be dead. Now, I say that because a lot of businesses, when they first start out, their network looks very similar to a home network, and they make some big boo-boos, some very big mistakes. Let me show you what it might look like. So, Network Chuck Coffee, still a very young, small, growing coffee company. And let's say I trusted a noob to install my network. I would never do that. But let's say I did. Very similar to your home network, I'll have a router. Although in your home network, your router isn't just your router, it's also your switch, your modem, even your WEP. No, not the song, a wireless access point. This is a networking video, get your head straight. So it's doing a lot, which is a horrible thing. You don't want to have one device doing everything. And we'll get into why that's important here in a moment. But for now, my coffee company just has the router, and my router connects to a switch. And honestly, for a small business, this is fine. I've got my computers connected to my switch. I'll have a WAP, the wireless access point, connected to it as well, giving me Wi-Fi to all my people, maybe a few phones, and then of course my server to run my website. Well, hold on a second. My switch only has 24 ports. I'm out of ports. I have more things to connect, more computers, more servers. What do I do? Well, I tell my noob network engineer to fix it for me. And this is where the noob really screws up. What does he do? Well, he gets another switch. Which is fine. He does a great job getting that. Here it comes. And then he connects the switch to the switch, and then, hold on, what did you do? Hold on, what did you do? This is bad. I'll explain why here in a moment. And before long, I'm growing like crazy, so I need to add another switch. My noob network engineer does another switch, and he adds it out here, and then he does it again. He connects this switch to that switch. Ooh, I'm sure a lot of you, if you know networking, this is probably scaring you. It makes me just have heart palpitations just thinking about it. This is bad. Now, it works. Don't get me wrong. This totally works. But then this happens. My pug Moses comes over and starts chewing on this cable right here. Then suddenly, boo, the cable breaks. And then what happens? Well, all the devices connected to this switch, and this switch, they're gone. They can't connect to anything, right? They're down. This right here is what we call, now say it with me, a single point of failure. Don't ever have those in your network ever. All of these right here are single points of failure, which basically means if one thing fails, then most of your stuff goes down. Never want to have that. Now again, this design still works. You might have something like this in your house. There are a lot of businesses that have this, and it works most of the time until something fails. In your home, you can afford it to fail because the worst thing that can happen is you miss an episode of Netflix, or worse, you can't watch my next video, whatever. But in business, that means dollars and cents. That's money, time. Now I'm showing you this because you will see this in the wild, in the real world, and you have to tell them why it's dumb, and you have to fix it. So how do we fix this? What do we do? Well, some might think, well, you know, we have those single points of failure. Let's just add another connection. We could do that. Add another cable here. Another cable here. That's better, but what if the switch goes down? What if this switch goes down? We still have glaring problems, and this is not ideal, which is why we have two designs I'm going to talk about today. It'll help us become redundant, and you'll hear that word a lot when you're talking about network design. You want to remove as many single points of failure as you can, so you want to be able to have a cable go down, but things still be up. A switch goes down, but things still be up. Let me show you what that looks like. So daisy chaining our switches together? Bad. Don't do that. So what do we do? How can we make this better? Well, we could do this. Watch.
How can you make it better? Do you still remember? Yeah, I think so. Okay, you think so? Are you gonna explain it or? Sure. Okay, so we'll redesign it. This is our router, Odyssey. I would say you put your switches here, connection here. If this link goes down, you still have this one to use, and this one if this switch goes down. That's better. Now, of course, you need SCP, but
Watch. Let's put the router right here, and instead of daisy chaining, we just connect our switches to the router. Each one. Done. That was easy. Come on, Chuck, you're making it sound so hard. Well, we're not quite done. Now, this will work, but it's not ideal. So, for example, my computers. This works great for when they want to get to the internet, because that's what the router is great for. Layer 3. But my computers and my servers aren't just talking to the internet. They're talking to each other. They're talking on the same network. And that's where the router becomes less ideal, and he's not the best guy for the job. So what we want is another switch, but not just any switch. Oh, you're going to love this. This is something when I found this out, I'm like, mind blown. So we're going to scooch the router up here for a moment. He's still in play, but we're going to talk about something different. Watch my previous videos. We know that switches, they deal with layer 2 MAC addresses, and routers deal with layer 3 IP addresses. What's a layer 3 switch doing here? That's sci-fi, that's weird, I can't deal with that. No, it's amazing. But it's not just any switch. On this out, I'm like, I'm gonna bring in this guy right here. What is that? It's a switch. But it's not just any switch. This, my friends, is a multi-layer switch, often referred to as a layer 3 switch, which might sound weird if you watch my previous videos. We know that switches, they deal with layer 2 MAC addresses, and routers deal with layer 3 IP addresses. What's a layer 3 switch doing here? That's sci-fi, that's weird, I can't deal with that. No, it's amazing. It's literally a switch that can deal with IP addresses and MAC addresses. It can do it all, and it's blazing fast. And then our multi-layer switch will connect to our router, and we're looking a bit better right now, aren't we? I mean, it's really beautiful. If this connection goes down or this switch goes down, then these two are still up. This computer's still up, this server's still up. It's better. Beautiful. And
it's slightly better.
Two designs I'm going to talk. Whatever. But in business, that means dollars and cents. That's money, time. Now, I'm showing you this because you will see this in the wild, in the real world. And you have to tell them why it's dumb. And you have to fix it. So how do we fix this? What do we do? Well, some might think, well, we have those single points of failure. Let's just add another connection. We could do that. Add another cable here. Another cable here. That's better, but what if the switch will go down, but things still be up? A switch goes down. Easy? Come on, Chuck, you're making it sound so hard. Well, we're not quite done. Now, this will work, but it's not ideal. So, for example, my computers. This works great for when they want to get to the internet, because that's what the router is great for. Layer 3. But my computers and my servers aren't just talking to the internet. They're talking to each other. They're talking on the same network. And that's where the router becomes less ideal, and he's not the best guy for the job. So what we want is another switch, but not just any switch. Oh, you're going to love this. This is something when I found this out, I'm like, mind blown. So we're going to scooch the router up here for a moment. He's still in play, but we're going to talk about something else here. We're going to bring in this guy right here. What is that? It's a switch. But it's not just any switch. This, my friends, is a multi-layer switch, often referred to as a layer 3 switch, which might sound weird if you watch my previous videos. We know that switches, they deal with layer 2 MAC addresses, and routers deal with layer 3 IP addresses. What's a layer 3 switch doing here? That's sci-fi, that's weird, I can't deal with that. No, it's amazing. It's literally a switch that can deal with IP addresses and MAC addresses. It can do it all, and it's blazing fast. And then our multi-layer switch will connect to our router, and we're looking a bit better right now, aren't we? I mean, it's really beautiful. If this connection goes down or this switch goes down, then these two are still up. This computer's still up, this server's still up. It's better, right? And I'm sure you're thinking, well, Chuck, we still have this right here, this single point of failure. Yeah, we'll get to that. We're taking baby steps, and you'll encounter this a lot when you design networks for businesses, because designing a network with limited single points of failure can be crazy expensive. The more devices you add, the more the bill goes up. So I'll show you how we can fix this single point of failure here in a moment, but just know, the more we add, the more it costs. You'll have to work with the business and what their budget is. Now, this architecture, this model here, the way we designed our network is called a 2-tier architecture. Let me show you the tiers right now. Here's tier number 1 and tier number 2. The switches in this tier 1 are called our access switches, and we'll call this layer our access layer, because they give our devices, the things we connect to our switches, where'd my cables go? Hold on. Things like Raspberry Pis, giving them access. Ooh, that sound. Let me add a Pi in there real quick. Can't not have a Pi, Raspberry Pi in my network here. What am I, crazy? There we go, much better. And then our tier 2 layer, this guy is called our distribution layer. And of course, this would be our distribution switch. Why is he called that? Well, because his job is to distribute all the packets, all the frames throughout the network. Like, he's it. Everything goes through him. If the computer wants to talk to my server, well, the computer goes access switch, distribution switch, down to access switch, down to server. If he wants to access the internet, access switch, distribution switch, router. Now, because everything goes through him, he's got to be pretty bulky. He's got to be, He's got to be big. Now, what do I mean by that? Well, think about computers. This Raspberry Pi, while he's awesome, he's not like a computing powerhouse. He's tiny. You're not going to be playing Call of Duty on this guy. Well, not yet. You never know. He's not powerful enough. And the same goes with switches. If you got a tiny little 8-port switch, he can only handle so much traffic before he's like, I need help. So don't put a tiny little 8-port switch in your distribution layer. He'll die. In the distribution layer, you'll want a massive switch with a lot of horsepower. And just like a computer, it'll have more components, more expensive hardware to make it faster. Now, I've shown you access layer switches. It's something like this, but distribution layer switches are a whole other beast. Emphasis on beast. Let me show you one real quick. Here are a list of Cisco switches that could be considered distribution layer switches. And you've got options. And it all depends on what you need and really how much you can spend. So like right here, we have the Cisco Catalyst 3850s. They have a very similar form factor to the access layer switches, but they can handle a lot more. Like look here, 480 gigabits per second on their backplane, which means they can handle that much traffic going through them at once, which is a lot. But of course, if you need more, you can get more. You go to the Cisco Catalyst 6500, you got 11.4 terabytes per second, or terabits per second. And look at that thing. It's crazy. Look at that guy. And we'll cover more about these guys here in a moment because they can go bigger and have a different role. We'll touch on that here in a moment. Now, we haven't gone too deep down the Cisco rabbit hole just yet. We will, don't worry. So I kind of glossed over what the distribution layer is responsible for. It does more than just distribute. Like, let's take a field trip over to the Boson Courseware real quick. You'll want to get this stuff. I've got their courseware open. Now let's learn about the distribution layer real quick. If you want to get this, I got a link below. Now, I didn't mention this before, but the distribution layer is sometimes referred to as the aggregation layer. Let me highlight that. That's the worst highlighter ever. Better. Okay. What it does things like route filtering, inter-VLAN routing, management ACLs, IPS, security policies, routing, because remember they are layer 3, and then summarization and next hop redundancy. I said a lot of words that we have not covered yet. We will. Just know that those are the roles that the distribution layer typically has, or the ones we give to it. Now there is something I skipped over. You may have noticed this. Because the distribution layer is the intermediary between the access layer and the core layer. What's the core layer? I didn't talk about the core layer. Well, if I scroll up just a little bit, look at this. There's another layer? What? What is that? We'll talk about that. Right now we're only looking at the distribution layer and access layer, which is called the two-tier architecture, and we'll touch on it here in a moment. Now let's talk about these other single points of failure. How can we fix things? Well, we can add more devices, right? Like check this out. I can add one more distribution layer switch. We'll do that. Scoot him over right here, and we'll connect our switches, so it might look like this. We'll add one more connection, one more connection, one more connection. Then of course we'll connect our switch to the router, and then we'll even connect our two switches to each other. This is what I'm talking about. We've got two distribution layer switches, so no longer a single point of failure. We've got two links to each switch. That's amazing. And then we have two connections to our router. But wait, hold on. We still have one router. We can solve that. Let's solve that right now. Let's put in one more router, and we'll connect both switches to them. Man, look at all that redundancy. It's beautiful. But it's expensive. This is ideal. A lot of companies aren't willing to pay that much for stuff because these, I mean, oh my gosh, these layer 3 switches, they could be like hundreds of thousands of dollars. Same for the routers, just depending on how big you go. No one said networking is cheap, which is why we make the big bucks. Now, this 2-tier architecture isn't the only kid on the block. Now, let me show you where a 3-tier architecture might come into play. Let's say Network Chuck Coffee really just starts booming, like, oh my gosh. And we have to add more buildings just to hold all our people. We have so many people now. Now we have 3 buildings, things are booming, it's amazing. But we need to connect our buildings together so we can all, have a network. That's what we're doing here, right? All right, let's connect my multi-layer switch to my multi-layer switch down here, my distribution layer. Same thing, let's go over here, and let's do it right here. Just random, hey, we got connectivity, right? But let's make sure we add in some redundancy. We'll also add redundant links. Make sure each switch has a connection to each switch, and each location has a connection to each location. Okay, we did it. It's kind of a mess, but we did it. We have another building coming in. Okay, get ready, guys. Gotta hire some more network engineers. All right, so let's connect them. Here we go. Okay, this is getting a little crazy. As big as our distribution switches are, they're under fire right now. They can't handle all this stuff. Too many connections, they're running out of ports. We're maxing out the bandwidth. What do? Let's go with a 3-tier architecture. You saw that coming, right? Let's do it. Get all those connections out of there. Whew, stressing me out. We're gonna add one more layer here, so let's get our routers out of here. Or scoot it up, we're not gonna get rid of them. And we'll put our next layer in. And this layer will have a beast of a switch. It will also be a layer 3 switch, but this will be the big daddy. He'll be so powerful, so awesome. He can handle all that traffic. This switch is our core switch, and this is our core layer. Tier 3. Our distribution layer switches will connect up to him. In a perfect world, we'd have 2 of our core, because he's the main guy. And we connect them up, and our cores will be connected to each other, and then we'll connect our routers to our core switches. This is a beautiful, lovely campus network design. Oh, so good. Expensive, but good. Okay, now what's this core layer doing besides just being awesome and powerful and huge and Let me show you. Let's go look at Boson. So the access layer, we know he's connecting our devices, our phones, our computers, everything. He's the access layer. Distribution, we just talked about him. Now the core layer, what is he doing? Look how short his paragraph is. That is truly sums it up here. He's like that massive guy at the gym, just, is grunting. That's all he does is grunt and lift. That's what this guy does. He's just fast. and he's associated with low latency and high reliability. So the core switch is expensive, reliable, and beefy. Because he is the network backbone and a ton of traffic goes through him, he has to be able to handle a lot. The weight of the network's on his shoulders. So this is our Cisco 3-tier network design model. Core, distribution, access. Now I want to talk real quick about the 2-tier. The 2-tier had the core layer gone. But no, hold on. He wasn't gone. He was still there, or his role was still there. That just became the job of the distribution layer. Let me show you real quick. We'll scroll down through Boson's amazing courseware and get to the Cisco 2-tier network design model. Notice what they call it, the collapsed core layer. This model is often referred to as the collapsed core model. I don't know what happened to my D there, just ignore him. But the functions of the core were collapsed into the distribution layer. So the distribution switches have all the responsibilities of the distribution switches, right? They have to do a bunch of the routing, the inter-VLAN routing, access control lists and such. Like they do a lot. And then they have to also be the backbone of the network. They have to be powerful and crazy, which in most cases is A-okay and fine. I've seen more collapsed core or 2-tier models than I've seen 3-tier. 3-tier is fantastic for what I'm about to show you right now. Looking back at our 4 buildings here, here's our new design with a tier 3. Notice that only one of the buildings has the core layer, the tier 3 layer, and that's the design, right? The core layer is the core for the entire campus. So now you can imagine how this might simplify things. Our distribution layers will connect back to our core layers, but just to the core layers, not to each other with that full nasty mesh like we had before. This allows us to scale a lot easier if we have a massive campus. So this is a bit better. My drawings are horrible. Let me show you a better view from Cisco's perspective. Cisco has great documentation. Here's how buildings will connect without a core. We just saw this, just a mess. It's so not scalable, right? It's too complex. But if you scroll down just a little bit, here's our core, and it solves a problem. It's beautiful, a lot more clean. We have our one core, then we have all our tier 1 and tier 2s in our buildings. Now, you want to see a core switch and how big it might be? Looking back at Cisco's available distribution and core switches, that's what this is called. Find the best core and distribution switch for you. If you are on the far right, it's the smaller stuff. If you go to the very far left, you get bigger and bigger and bigger until you get to the big daddy. The Cisco Catalyst 9600 series. This thing's a beast. They're modular, so you can just slide in extra little features and awesomeness. They've got redundant everything, and look at the available backplane or bandwidth it has, 25.6 terabits per second. It's pretty crazy. If you want to see one of these, actually, David Bombal and I went to Cisco headquarters in San Jose, and we got to talk with the guys who designed it. They walked us through it, so I got a video below if you want to check that out. Actually, I'll play a clip right now.
Okay, discuss everything that you just consumed. Alright. So talk about everything. Okay, so we know that there's layer 2 and layer 3 designs collapsed, and, well, layer 2 architecture, collapsed core, and 3-layer architecture. So why do we do this? The main answer is redundancy. So when you work at an office, which I suppose would be a business, time equals money. Yeah? So, the more redundant, like, it's essentially all about points of failure, okay? This is the entire goal. A bad network is designed like something like this. Why is this bad? And then maybe here we would have the router. It's bad because if this link goes down, essentially your entire network, your servers that might be located here, and your workers that are here, all of them are cut off, okay? Because, well, this is your access to what? The internet, to your clients. So this is literally a single point of failure for the business. Now, like for the entire business, right? Like, yes, if you create this design, a small upgrade, now the entire network does not have a single point of failure, but it's still subpar. Subpar, like, still, to be honest, for the server itself, there is a single point of failure. If this link goes down, it's over. What if this link goes down? Well, that's your final connection. You can't really, you'll always need that. There's not really a way around that. I mean, what if you have multiple connections? I guess that's probably a thing, yeah. But if you have this type of connection, then that's all it is. So, like, if you're asking why do we do this, we do this such that our client can still access our server if something goes wrong. Like, depending on how critical your service is, like, imagine if YouTube is down for like 5 minutes, the server. Well, YouTube does not have a single server. It has a massive fucking cluster of massive fucking reliable servers. Each probably in some kind of, this is often used in databases. Probably like 3 massive, this is just one server room or something. Let's stop giving it the... And instead of like this, one connection, they're connected like... Well, no, that's not really true. Sorry. Is it? I think it is. Yeah, well, I think it is. Are you tired?
Much traffic before here, and we'll connect our switches, so it might look like this. We'll add one more connection, one more connection, one more connection. Then of course...
Yeah, probably not. Maybe this one is connected to 2. But then the answer is not always more. No, it's not. Of course not. Like, you can't just... If you're doing 3-layered design, how do I say this? If you're trying to scale that, well, you should do 3-layered, not 2-layered, because you need those core devices to be able to handle that. Like this type of shit. Not this. You know, all interconnected. It becomes it doesn't become scalable anymore.
Of course, we'll connect our switch to the router, and then we even connect our 2 switches to each other. This is what I'm talking about. We've got 2 distribution layer switches, no longer a single point of failure. We've got 2 links to each switch. That's amazing. And then we have 2 connections to our router. But wait, hold on. We still have 1 router. We can solve that. Let's solve that right now. Let's put in 1 more router, and we'll connect both switches to them. Man, look at all that redundancy. It's beautiful. But it's expensive. This is ideal. A lot of companies aren't willing to pay that much for stuff, because these, I mean, oh my gosh, these layer 3 switches, they could be like hundreds of thousands of dollars. Same for the routers, just depending on how big you go. No one said networking is cheap, which is why we make the big bucks. Now, this 2-tier architecture isn't the only kid on the block. Now, let me show you where a 3-tier architecture might come into play. Let's say E-tier network design model. Core, distribution, access. Now, I want to talk real quick about the 2-tier. The 2-tier had the core layer gone. But no, hold on. He wasn't gone. He was still there, or his role was still there. That just became the job of the distribution layer. Let me show you real quick. We'll scroll down through Bozon's amazing courseware and get to the Cisco 2-tier network design model. Notice what they call it, the collapsed core layer. This model is often referred to as the collapsed core model. I don't know what happened to my D there, just ignore him. But the functions of the core were collapsed into the distribution layer. So the distribution switches have all the responsibilities of the distribution switches, right? They have to do a bunch of the routing, the inter-VLAN routing, access control lists and such. Like, they do a lot. And then they have to also be the backbone of the network. They have to be powerful and crazy, which in most cases is A-okay and fine. I've seen more collapsed core or 2-tier models than I've seen 3-tier. 3 tiers fantastic for what I'm about to show you right now. Looking back at our 4 buildings here, here's our new design with a tier 3. Notice that only one of the buildings has the core layer, the tier 3 layer, and that's the design, right? The core layer is the core for the entire campus. So now you can imagine how this might simplify things. Our distribution layers will connect back to our core layers, but just to the core layers, not to each other, with that full nasty mesh like we had before. This allows us to scale a lot easier if we have a massive campus. So this is a bit better. My drawings are horrible. Let me show you a better view from Cisco's perspective. Cisco has great documentation. Here's how buildings will connect without a core. We just saw this. It's just a mess. It's so not scalable, right? It's too complex. But if you scroll down just a little bit, here's our core, and it solves a problem. It's beautiful. A lot more clean. We have our 1 core, and then we have all our tier 1 and tier 2s in our buildings. Now, you want to see a core switch and how big it might be? Looking back at Cisco's available distribution and core switches, that's what this is called. Find the best core and distribution switch for you. If you are on the far right, it's the smaller stuff. If you go to the very far left, you get bigger and bigger and bigger until you get to the Big Daddy. The Cisco Catalyst 9600 series. This thing's a beast. They're modular, so you can just slide in extra little features and awesomeness. They've got redundant everything, and look at the available backplane or bandwidth it has, 25.6 terabits per second. It's pretty crazy. If you want to see one of these, actually, David Bombal and I went to Cisco headquarters in San Jose, and we got to talk with the guys who designed it. They walked us through it, so I got a video below if you want to check that out. Actually, I'll play a clip right now.
File deed.
Oh yeah.
That's nice.
That feels high quality.
That's nice.
Wow. You see that they are hefty, and so that's also another future proof for delivering power.
They had just released it, and they let us take a look at it and play with it. Crazy. Now, as I mentioned before, this model right here is the one I've seen the most of. It's what I've worked with the most. The collapse core, where you have your access layer doing its thing on both sets of designs, but then you have your collapse core. The distribution switches also being the core switches, and then these switches will connect up to your routers. When we're looking at tier 3, I love looking back at that Cisco example. This is why you want to have a tier 3. When you have a bunch of buildings in a campus, they all need crazy high-speed connection to each other like they're all in the same building. So we call it a campus, and really where we got the term from is like a college campus, a school campus. I went to Cisco's campus, and they have like a bajillion buildings. I got lost multiple times, and they have stuff like this. I mean, they invented it, right? So they invented it because they probably needed it. But what I found is most companies I've worked for, we have one main corporate office, and we had our core distribution switches connecting to our access switches, and that's all we needed. Now, that's just the campus. That's connecting our people and our users in the same building. We have more than that, though. We also have data centers and how we design our data centers. We have cloud and how we design our connections to the cloud. We have our WAN. We have our small office, home office. We have our users, all kinds of different things. We're going to talk about all those here in the next few episodes. Now, I've got some homework for you. Here's what I want you to do. Most of you work for a company, right? You may be in their IT department. You may not be in their IT department. Doesn't matter. What I want you to do is find out what design they have. Is it 2-tier? Is it 3-tier? Is it some weird tier? I don't know. Find that out and let us know in the comments below. I think that'd be really fun to see everyone's design in their network. And that was episode 6. Let me know what you think. Comments below. If you have any questions or just suggestions, let me know. Or if you need help, let me know as well. And by the way, did you know I have a Discord community? Discord's a place where you can go and get help. I've got about 14,000 people in there right now willing to...
Well, okay, so anything that I need to consider and really kind of... I would say this is one of those topics that I struggle with the most because it's very real world. Like, I mean, it's literally a representation of how networks work in the real world with their layers and I don't think it's stuck there, I think. I think one of the core things to remember is, like, the principle of a network that's supposed to be reliable is redundancy, the core principle. And, like, if you're a business and you have all-in-one situation, now to be fair, it depends, like, but it's, the core principle is, like, if you are a business, you should not just have all-in-one consumer-based device which has a router, switch, modem, WAP, you know, not the song, Renge. Wireless access point all-in-one. But you should have at least a 2-layer architecture, which is your collapsed core architecture, which is what most, like, I mean, it makes sense. Like, the 3-layer is just a bit much. I mean, like, what the fuck are we even offering at this point? Is that what data centers use then? Good question. Well, it's a complete mesh usually in data centers. There's absolute redundancy. But yeah, just create your access switches, which their core function is providing access to the network. But why, like, if you're like someone, yeah, but why have all these different functions for these devices? Like I said, points of failure. If you separate access and then distribution and core for 2-layer architecture, essentially, if one of these switches goes down, well, switches goes down. That's more critical than if a single link goes down. If a switch goes down and the device connected to it, obviously usually with a single connection, then it's over for that connection. But say you only have one switch. Not only that, it doesn't go down for that one device connected switch. It goes down for every device connected to that switch because it's all they have. Do you understand? This is essentially, I guess, a network engineer at its core is trying to get to this question of like, hey, I have a business. Can you help me set up my network? Now, obviously, like it's not like this is, and they want budget, they want time efficiency, they want it set up quickly, and they want it to be done relatively cheap. That's the core of what they want. So, I would almost argue that your network topology skills, identifying and knowing, like what he said right there, that's a fucking really good skill to like kind of, like bro, if you're a network guy, go around in random places, figure out what network they have, try like literally in practice identify flaws, security flaws, redundancy flaws, like in general there's flaws. Why, like, you have to think, is it resistant to a fucking baby? Is it resistant to a pug? Is it resistant to fire? Like, this is where, what's it called? PLC cables, I think, which are used on roofs a lot and stuff, I'm pretty sure, come into play. My home network might be the least redundant thing in the world. It's like right by my bed. It's like, I sometimes have water nearby. It's fucking dangerous as fuck. They haven't gone down yet. Yeah, and that's not, doesn't matter. Like, bro, you want, when you have a business, you have a lot of devices speaking at layer 2 together. If you want efficiency, speed, you want them connected at layer 2, which just means we send frames. Frames, we remember, has a header and trailer. They're encapsulated like that. Remember to think of encapsulation just as a conceptual thing, as just like a literally like things encapsulated. Like you have layer 7 inside, you have layer 6 inside, you have layer 5. But when we send it, no, sorry, that's wrong. What am I saying? I don't know why I said it like that. Sorry. Zoom out. I'm sorry. I meant when we encapsulate, we have 7 inside, then we have 6 around that, then we have 5 around that, and then we send it as a frame, not the opposite. See how I still get tripped up by that? Like fucking retard, bro. There's that. And, yeah.
To help you out with whatever you're doing. Look for a job, need help with CCNA, we got you. Link below to join that. And did you know I'm on social media? Are you following me on Instagram?
About Discord, I'm gonna get Discord back just to get into a bunch of computer networking Discords. It's the easiest way to almost get like what do you call it? Help desk training, like, which is one of the first networking jobs often people get. I know it's kind of goofy, but pays okay, and yeah. Easiest way to get practice for that, like, because again, I like to put, I did that before for CCNA. I said to myself at some point, every question that comes in here, try to answer it yourself. And user questions are often very tricky because they add like these unexpected variables, like bad grammar, questions that don't even make sense. So you have to kind of make sense of the question itself, and then you have to try to answer what he was trying to ask. And there's like multiple variables. It's more real world-esque. So I'm probably gonna get Discord back just to join a bunch of computer networking and also crypto groups that I think are somewhat valuable for learning. And again, when I say learning for crypto, there's 2 skills that I think are useful that I'm trying to get better at. Utility research. So I believe in crypto, you will always be able to make money in the medium to long term, right? Like multiple months or years even. Trading utility and holding that if you think it could do well and You get better at researching, reading, understanding community behind a token, why something did well. I actually think trading meme coins is a skill too. Like, you can do that. But that's where I get into query trading, which is something that I try to get better at, which is like DRPT is a tool I use, and yeah. I think I'm about to go on a walk after my stream here.
Instagram, Twitter, Facebook, LinkedIn, everywhere. Why? So go follow. Everything is Network Chuck, at Network Chuck. I post there sometimes, so go follow me sometimes. And if you want to help me do more of this, creating free training on YouTube, creating low-cost courses in other places, you can join my membership, become part of the team. You can either join through YouTube at the join button below, or go sign up at thisisit.io. I got links below for everything. Or my Patreon. I got a Patreon as well. Oh, and don't forget to enter the Boson contest. I'm giving away 3 copies of their NetSim for CCNA and their new courseware for CCNA, and it's amazing. So contest is ending like soon, so you better hurry. And if you're too late and you didn't win, no worries. I got a special link below. You get 15% off. Have you ever been inside a data center? It's amazing. Rows and rows of switches, routers, servers. Have you ever been inside a data center? It's amazing. Rows and rows of switches, routers, servers, just buzzing and humming, powering the internet we use every day. Whew, getting goosebumps just thinking about it. And as you're learning networking, you've got to wonder, how does all that work? What does a data center network look like? Is it different from any other network? That's what we're talking about today. How do network engineers go about designing data center networks? And also a huge shout out to Boson Software for sponsoring this video. They are the official sponsor of this course. They help make it free here on YouTube, and they just happen to have the best prep software out there for the CCNA. If you need labs, exams, courseware, they got you. Check it out, link below. Now, data centers are different, right? Like if you look at a corporate office, you got people trying to connect to things and the internet. A data center is all about servers connecting to things and the internet. But for a long time, we've kind of designed their networks the same way, with the same model. But first I want to start with this. What exactly is a data center? What's the purpose of it? And also, when will you get to work on a data center? In what situation would you have to step into one and do stuff in one? Which you probably will. If you're going down the networking path, you probably, it's going to be awesome. Like, I'm so excited for you. I remember my first time in a data center, and it was nothing short of magical. Felt like I was at Disneyland. Now I'll start with this. Pretty much any resource you access over the internet or just in a network period is going to be inside a data center. And you've seen data centers before, either on TV or what I just showed you earlier. I mean, here's one. I'm actually doing a 360 tour of Google's data center. Just rows and rows, racks and racks, full of servers, routers, switches. Like I said, Disneyland. So like right now, you may be watching me on YouTube, and this is a Google data center, so you might be watching me from this server right here. It's streaming to you from here. Okay, big companies like Google have data centers. Facebook has data centers. Massive data centers. Amazon, Microsoft. And if you join their network team, you might get access and be able to work inside those. But what about other companies that aren't as big as Google, Facebook, or Amazon? Do all companies have and use data centers? The answer is yes, but not all in the same way. So let's say we have Network Chuck Coffee. Get yours today. Network Chuck Coffee sells coffee online through a website that lives on a server. So for me to offer that service to you, I got a few options. I could open up my own data center, which doesn't always mean having a massive warehouse with rows and rows of servers. It might just be one room with one rack, which is what I have in my house. I've got my one rack of equipment, some routers in there, switches, servers, and you can access my
Wouldn't you say that's a server and all that
stuff
stuff?
directly from my internet connection. A lot of small to medium-sized companies do have a situation like this. One of my first ever jobs doing network engineering, they, on their first floor of their building, had a little small networking closet that was like a data center. It had 3 racks full of servers, routers, and switches. And that was our web presence. That's where we ran our websites. That was everything. Now, maybe my home internet connection isn't great, or I don't have adequate air conditioning and a raised floor, and I don't have everything to meet the standards I need to actually run a company. Well, then I might want to put my stuff in a real data center. And they do offer all those things. Redundant cooling, redundant power, all things you need if you're going to run a company. So I would rent space in a data center instead, or rent racks. This is what the majority of the companies I work for have done. Now, this will look like one of the larger data centers. It'll have rows and rows of racks of servers and stuff, but they're from different customers that the data center has. You might have Joe's Zebra Farm over here, Bob's Biscuits right here, and the Network Chuck Coffee over here. You can rent, 2, 3, 4, maybe a couple rows of racks. And so you put your servers in there, your routers, your switches, and the data center would provide you with power and internet connection. Now, what I actually do for Network Chuck Coffee is I use the cloud. The cloud still involves a data center, but it's someone else's data center and someone else's servers. So Amazon, AWS, Google Cloud, Microsoft Azure, they offer their servers and their data center to you as a service. You don't need to rent space or have your own hardware or anything. You just say, click, I want my website to be right there, and it happens. So now when we talk about data center network design, if your company's fully cloud, which is rare, if they're all in the cloud, you don't really have to concern yourself with how they design the network because they handle it for you. Unless you're a network engineer for one of these cloud providers, then You know all about this. And we'll cover how they do it because it's not very different from how you would want to design your data center up here. So if your company has its own data center in its building, or they rent rack space in another data center, this is where you come in. And you have to know how to design a data center network. And again, a lot of companies have this situation. They actually might have a combination of all three of these here. The first company I worked for did have this, but they eventually did rent space in another data center. We retained both of those, and we added stuff to the cloud. That's called hybrid cloud. And that's a whole other video. So let's talk about how you should design your data center network. So this is what I would do if I were designing my network chuck coffee data center traditionally, the old way. Let's say I rented a bunch of rack space in a data center. I have all my racks here. Each of these racks would have a bunch of servers doing all kinds of stuff. Websites, databases, and for the network. In each rack, I would have 1 or 2 switches right at the top. We actually call these our TOR switches. Nothing to do with the dark web. It stands for top of rack switches, TOR. Because yeah, it's at the top of the rack. And the servers in each rack will connect to their switch. Now how do all these servers talk to each other and get to the internet? Well, I'd have my next layer, my distribution layer. If you watch my last video, this might start looking a little bit familiar to you. Our top of rack switches, which we could also refer to as our access layer switches, will connect to our distribution layer switches, redundant connections, as we should have. And then we'd have another layer of switching, our core switch, our big daddy beast, which I know looks like a building, but this is a switch. It's a switch. A multi-layer switch. And that's what our distribution layer switches would connect to. Access layer, distribution layer, or aggregation layer, and our core, or our core layer. Now just so you know, the distribution core layer in a real data center would not be out floating in the air like this. They would often either be in their own dedicated network rack, or maybe resting in some extra space in one of these racks here. Now this is bothering me. With the proper 3-tier design, you want to have some redundancy. So let me add another core switch here, which again is a beefy, massive chassis switch that costs a ton of money. But you gotta have it if you're going with this design. That way we have some redundancy, some resiliency. Then if we had more racks in that data center, or for like Facebook and Amazon.
Interesting. (2013).
Engineer, someone who not only knows how to, get in and configure a basic router or switch configuration, but knows how to troubleshoot and actually design a network that works. I'd say it took me about 3 years before I felt like I was an engineer actually designing something. Now, what did that involve me doing? Well, first of all, I was studying a lot. I was studying like crazy, and I was also working crazy hours. I mean, you can ask my wife. Don't ask her; she'll get angry about it. But I was working late nights. I was at data centers doing stuff. I was studying a lot. I mean, it was a lot of work. That's when I considered myself a network engineer. Now, a lot of you, when you ask that question, how long does it take to become a network engineer? You're probably asking, how long will it take for me to get my certifications and actually get into a role where I'm working with network stuff? That depends too, but I would say it won't take you very long if you do the right things. The typical path you'll take from zero to network engineer will be finding like an entry-level help desk position, right? And there you're not going to be doing much networking. You'll be dealing with PC issues and people calling in, and it'll be basic stuff, right? Nothing serious. What you're wanting to do is move up from that help desk position to the network admin or junior network admin or network engineer position. That, I think, will not take you very long at all. For me, to go from just PC troubleshooting to working with Cisco router stuff, it took me about 6 months. Now, how did I do that? Well, it's pretty simple, guys. First of all, be studying and be very vocal about your studying. So what I mean is I was working on my CCENT and then later my CCNA. I let everyone know I was working on it. I let the network admins and network engineers know I was working on it. So yeah, I was on the help desk, but
This is big, man. Like, even my wagey job, I remember like the only shift that made me or gave me the chance to work as a machine operator there, like a VSK machine, sorry, which is a Hagla machine. It was because it is the hardest part of the factory. I simply said, I remember, and verbally I saw interest because it was genuine. You can't lie about stuff, but if you kind of in a humble way explain what you're doing and what you do, your ethos just explodes. So I said, I studied computer network, and I did. Isn't bullshit. I mean, I guess he assumed I did it in college or something, but and I then said, no, I did my CCNA. I don't know if he knew what that was, but instantly he's like, oh, that guy is not dumb. He's pretty smart. Because people are just very simple. People work off basic verbal communication. Like if you say, I study this thing, but it can't be braggy. And if I work as like a help desk or something, and if I want to rise the ranks, I do my job with diligence. You do your job with diligence, and you, in a humble, somewhat way, somehow try to sneak in that you are studying CCNA or, from in my case, CCMP or CCIE is another one.
I was doing everything I could to get my hands on network engineering stuff. So the network admin in the company, I was his shadow, man. I was on him. When they would have maintenance weekends, which they do, because you can't make network changes during the day. People go down and all hell breaks loose. So no, they do the things. They do big changes, router upgrades, installing new routers, things like that over the weekend. I would stay late. I would go with them to the data center. No, I wasn't getting paid for it. It was pretty much volunteer work, but I was getting a ton of value out of that. I was learning. They were seeing the effort I was putting forth. So when it came time that they realized they needed help, who are they going to turn to? This guy, the guy who's been helping them, the guy who's shown interest, who is working hard. So how long it's going to take you to become a network engineer really depends on how much time and effort you're going to put into this. If you're just studying for your CCNA, spending a few hours a night, but you're not putting any effort in like marketing yourself or getting yourself into a good position to actually get your feet wet, you're not going to get very far. And you may be like, right now you may have no IT experience. You're not even on a help desk and you're just trying to get your CCENT, CCNA and get into that role. That's cool. I understand that. You're doing the right thing. But you can find opportunities. I would try to get on some sort of IT position as soon as possible, because that's the fastest way to get onto a network engineering role. But there are other paths. I've heard of people like volunteering, helping out schools or companies who can't afford to pay network admin staff. I've heard of things like that happening. So there's options. You gotta work at it. So I can only really speak from my experience and the things I've heard from other guys. But for me, it took me 6 months to actually start doing work with Cisco stuff. And this was, again, working pretty hard on that. I know guys who've gone through the Cisco Net Academy thing, and they'll complete that course and they'll get a job right out of the Net Academy. They have like these job situations set up, which is pretty cool. But I mean, a big part of it is just if you want to get into networking, you gotta network. And what I mean by that is it's really about who you know. You ask anyone who's very successful in IT, they'll tell you that a large part of being successful is who you know. So do your best to find some networking events. They've got the Cisco users group in certain cities. Look it up. They might have one there in your city.